Modern large language model agents are useful because they operate across multiple enterprise integrations in a single turn. You give the agent a natural language request, and it plans a sequence of actions: checking a calendar, summarizing a Slack thread, drafting a Jira ticket, repeating this tool calling loop until the task is complete. The agent relies on trusted inputs to define its parameters. The user's prompt provides the goal, and the developer's system prompt sets the operational rules. But the content the agent interacts with is entirely untrusted. It pulls responses from external channels, like inbound emails, shared wikis, or customer support tickets. To decide its next step, the agent must read this unverified external state back into its own context window. This architecture creates a structural vulnerability known as the read-write gap. Every integration the agent reads from is a channel an external party can write into. An adversary pre-stages a malicious payload in a location the agent is likely to scan, like an email body or a calendar invite description. The agent also has the authority to execute write actions across the enterprise, whether that's sending an outbound message or modifying CRM data. The attacker never touches the user's interface or the system prompt directly. The agent organically ingests the poison text during routine data retrieval. The user asks a legitimate question, and the agent reads the compromised data to answer it. Because the agent processes this content within its own reasoning loop, the adversarial instructions override the agent's logic mid-task. The compromise requires 0 clicks from the user. The adversarial content enters through a read on one integration, and the harm materializes through a write on another. As long as the agent unquestioningly processes tool response data into its context window, external actors can puppet internal enterprise actions. The most effective way to exploit this gap bypasses overt jailbreaks entirely. It relies on a class of attack called underspecified authorization. These attacks hide at the boundary of a user's request, exploiting instructions that admit subtle reinterpretation rather than issuing a blunt command. A user asks the agent to update a Salesforce note with Q3 progress and email the summary to the owner. The exact address isn't specified. Inside that note, an attacker has placed text formatted as a system audit log, routing summaries to a compliance relay address. This payload avoids aggressive commands, mimicking legitimate administrative metadata. Lacking a hard-coded address, the agent reads the note, extracts the progress, and accepts the mock audit log as the authoritative destination. The agent then executes the Gmail tool call, sending the internal summary directly to the attacker's external domain. Standard alignment training fails here because, from the model's perspective, it is successfully and helpfully completing the user's underspecified task. Measuring this specific class of integration vulnerability requires a dedicated framework. That is the exact purpose of AgentRedBench. Previous evaluation methods typically draw from a fixed library of attack templates. Replaying the exact same string every run fails to capture how adversaries adapt to different systems. Here, an attacker large language model generates fresh, context-aware payloads for every run. The orchestrator places this custom injection into a mock integration state. The target agent runs its tool calling loop, and an LLM judge scores whether the attack succeeded. This dynamic red teaming provides an accurate simulation of an adaptive adversary probing a complex SaaS architecture. Running this benchmark across 215 subtle scenarios against 8 frontier models establishes the unguarded baseline. This chart shows the attack success rates, spanning from 32% at the lowest end up to 81%. The Gemini 3 variants cluster at the top extreme, failing to stop the injection in roughly 4 out of 5 attempts. Conversely, Claude Sonnet 4.6 sits entirely alone at 32%, establishing the floor for model resistance. Within a single provider, Anthropic, there is a massive 47-point gap between Sonnet and Haiku. This variance indicates resistance to tool response injection is driven by alignment training, not simply parameter scale. Even the most secure models leave substantial room for exploitation, requiring active inference time defense. The standard approach to securing these systems is routing inputs through large open-source safety classifiers. These guards are trained on chat-style human dialogue. They are not exposed to the raw structural output of enterprise APIs. This scatterplot maps false positive rates against true positive detection. The ideal top left corner is empty for open-source baselines. LlamaGuard and PromptGuard sit at the bottom, blind to tool response attacks. Protect AI catches some, but its 25% false positive rate makes it unusable. A massive parameter count provides no security if the model's architectural lens is focused on the wrong target data. You cannot secure the integration layer with conversational filters. To counter this, researchers developed AgentRedGuard, a specialized countermeasure built to sit directly in line within the agent's tool calling loop. It is a 23 million parameter classifier, fine-tuned specifically on adversarial tool response data. It intercepts and analyzes tool response content, filtering out malicious instructions before the agent can read them back into its context window. A small model succeeds here because indirect prompt injection relies on specific structural patterns, like markdown wrappers or fake governance footers. The guard performs integration layer pattern recognition rather than attempting deep semantic reasoning. Tracking the attack success rate across the 8-model panel, deploying AgentRedGuard drops the 69.9% unguarded baseline to just 2.4%. This comes with only 9.5 milliseconds of CPU latency and a 0% false positive rate on production data. For engineers building production agents, the data is clear. Prompt safety filters will not protect autonomous systems interacting with external environments. You must close the read-write gap directly at the integration layer.